Welcome once again to another slide video from the Cornish Radio Amateur Club, and this is in the Foundation series leading to the Foundation exam and ultimately the Foundation license or M6 license. Let's have a look at the syllabus for propagation. So propagation basics is in the syllabus in section 6A, and 6A1 says recall that radio waves travel in straight lines unless diffracted or reflected. 6A2 says recall that radio waves get weaker as they spread out. 6A3 says recall at VHF and UHF, that's very high frequency and ultra high frequency, hills cause shadows and that waves get weaker in penetrating buildings, but glass windows are more transparent to radio waves. You must also remember from the section on frequencies what the frequencies are for VHF and UHF. Remember that HF is from 3 to 30 MHz, VHF is from 30 to 300 MHz, and UHF is from 300 to 3000 MHz. 3000 MHz is the same as 3 GHz. Recall that radio waves travel in straight lines and unless they're diffracted or reflected. Recall that radio waves get weaker as they spread out. Recall that at VHF and UHF hills cause shadows and that waves get weaker in penetrating buildings but glass windows are more transparent to radio waves. Recall that the range achieved at VHF or UHF is dependent on antenna height and a clear path and transmitter power. Understand that higher antennas are preferable to higher power as they improve both transmit and receive performance. Recall that outdoor antennas will perform better than indoor antennas. Recall that at VHF-UHF range decreases as frequency increases, and that in general VHF-UHF waves have a range not much beyond line of sight. And by line of sight we mean optical line of sight, how far you can see. And the final part of the propagation syllabus looks at the ionosphere, and that as the main mechanism for carrying HF waves. So recall that the ionosphere comprises layers of conductive gases at heights between 70 and 400 kilometers above the Earth. Recall that on HF, most communication relies on the waves being reflected by the ionosphere. And recall that HF can provide worldwide propagation depending on how well the ionosphere bends the waves back to Earth. Recall that this varies with frequency, time of day, and season. Now you may wish to do some additional study, so I would point you towards the crack training YouTube video, Background Radio Waves. That goes well beyond what is required for the Foundation exam, but it may provide you some context, especially if you are considering moving on to intermediate or advanced levels. And also you might like to look at the advanced propagation video. Remember, you only need to know what we've read out just a minute ago in the syllabus, so many items there will of course be beyond what you are required to learn. So let's get started. First point to note is that in free space, that means without any obstructions or any influence from objects either in the way or nearby, in other words in free space, all radio waves travel in straight lines. So here we have a signal going out from Earth to a satellite, and as it travels out it spreads out, but it doesn't gain any additional power. So the original power is spread over a greater area due to the spreading, and that is why at the receive antenna on the satellite, the power will be much less than if the satellite were closer to the satellite Earth station, shown in red. So in free space, all radio waves travel in straight lines, and radio wave weakens as it spreads out. Some people call this spreading loss. And many signals arrive at Earth. Now, whether they get to the surface of Earth or not is another matter, but from distant stars, many of them emit radio signals, and those interested in radio astronomy will be better qualified to talk about that. But they can be at all sorts of frequencies, and the signal will arrive at Earth, but it will also have suffered from the spreading loss, but is often detectable. Now, we've said that radio waves travel in straight lines unless something affects them. And so there are two main mechanisms that change the direction of radio waves. Now, the first is diffraction, and that's a bending of a radio wave as the bottom of the wave trips up. Now, we'll be looking at that concept, how the wave sort of trips as it moves along in subsequent slides. And reflection, the bouncing of a radio wave off a medium. Now, normally this might be a solid medium, but it can also be gaseous as well, or indeed liquid. Radio waves will bounce off the sea. And there are two mechanisms that reduce the intensity of the radio wave. We've looked at spreading loss, and we know that this is the spreading out of the radio wave with distance and the consequent spreading of the energy over a greater area. So at any particular place, the effect of the transmitted radio signal is smaller the greater the distance you are away from the transmitting source. And the second is attenuation. That's when a radio wave passes through a substance, it loses power. And if we remember back to the syllabus item there, they talk about an antenna being better outside than inside, but if it has got to be inside, it's better near a glass window than behind a wall. So that's a radio wave being attenuated, that's giving up some of its energy as it passes through a substance, and it would heat that substance almost imperceptibly, but the energy would probably be given up as heat energy. Let's go and look at those four mechanisms, two for changing the direction and two for reducing the intensity of the radio wave. Excuse me. So, longer wavelengths diffract over the ground and tend to follow the Earth's curvature somewhat. And here we're looking at how a radio wave changes direction. We're saying here that it depends on the wavelength, and we of course know that frequency and wavelength are linked. V equals F lambda is the formula. You don't need to know the formula, but you do need to be able to translate between frequency and wavelength using the chart on EX307, I think it is, given to you in the examination. So the longer wavelength, then, this is what happens. And if we look at the right of the screen, the wave fronts come in, and as they hit the hill there, they're tripped up. The bottom part of the wave is slowed up more than the top half, and so the wave is then forced to change direction. And so the wave coming in, if it had carried on in a straight line, it wouldn't have reached the house, but because of diffraction, it diffracts over the hill and reaches the house and comes to the receiving antenna. So that's refraction happening at a long wavelength. And broadcasters made use of this, and still do make use of this, with long wave broadcasts. Long wave broadcasts travel a long distance, and you can hear, for example, French radio stations where they are transmitting from France, which is obviously not optical line of sight from, let's say, us here in Cornwall, and yet we can hear them perfectly okay. So there we go. Longer wavelengths diffract over the ground and tend to follow the Earth's curvature somewhat. Now, shorter wavelengths diffract less and are more line of sight. LOS is the abbreviation often used. And here's a shorter wavelength, the shorter wavefront. It still trips, but not enough. And so we can say that it misses the antenna of the house and we don't get a signal. And so this is the concept then of the house being in the shadow of a hill. Now, a shorter wavelength such as VHF, that may well be the case. And amateurs using VHF become quite used to visualizing the terrain, the topography between two stations, and therefore understanding that there's a hill in the way and therefore they are or are not in shadow. So that goes into the syllabus point then of VHF waves have a range not much beyond line of sight. If we go over plain Earth here, we've got a radio link, or potentially two radio links, with three stations there, A, B and C. Now A is not optically line of sight to B, as you can see where it becomes a dashed line, it's obstructed by the Earth. So if you were at the top of the mast at A, you wouldn't be able to optically see the mast at B. But because of diffraction, you can just get a signal through to B. So VHF, UHF waves have a range a little bit beyond line of sight, but not a lot. Reflection is the second mechanism that we discussed for changing the direction of radio waves. Here we have two radio towers, I beg your pardon, on hills, and this is an over sea path. And they communicate perfectly adequately, but also another path exists with a reflection off the sea. And this can cause problems because the two path lengths are different. We don't need to know anything about this for the foundation exam, but later on in the intermediate and advanced exam, you will learn that this is a cause of fading. As the path lengths vary, they can arrive in phase or out of phase at the received antenna and will either reinforce or cancel out, and that variability is fading that can occur. So that's a reflection, and that's a reflection off the sea. You can also get reflections at VHF and UHF frequencies off hills and off buildings, and at HF, as we will see later on, a reflection off the ionosphere. We use reflections to our advantage in amateur radio with Earth, Moon, Earth. So some amateurs are very keen on this. It requires quite high powers and high gain antennas, but the signal is sent up and bounced off the moon, and you can achieve quite large distances using Earth's natural satellite. So EME uses the moon to reflect radio waves. Now, losses or attenuation increases with frequency, so the range therefore decreases with frequency. So losses are greater at UHF than VHF. Here we have a radio path between two antenna towers, and in between are some objects that are on their own not enough to completely obstruct the signal, because they're fairly narrow compared with the wavefront, and they are slightly porous from a radio wave point of view, but nevertheless they do attenuate signal. And if you look at that path there, going through some trees and with some buildings perhaps in the way, but not right across the whole wavefront, if you like, then we can say that at the higher frequencies, UHF, the losses are significantly more than VHF. So if we take that signal at 100 megahertz, it may suffer very few losses, so 100 megahertz being in the VHF band. But if we look at 3 gigahertz at the top of the UHF band, the losses may be so great as to prevent the signal being usable. So that's something to remember, that losses increase with frequency. Another point from the syllabus is more transmit power means more received signal. So here we have a signal there at the left. We can either send 1 or 10 watt. If we send 10 watt, the signal will be greater than if we send 1 watt. I think that's fairly obvious. The received signal will be greater if the transmit signal is greater. Higher antennas are better than more power. Here we have raised the antennas to be above the obstructions, and in general, using higher antennas is a better solution than simply turning up the power. So in the example we had previously, where we had a choice of 1 watt or 10 watt, if we also have a choice of raising the antenna, then raising the antenna is the preferable solution in general. And also in general, outdoor antennas perform better than indoor antennas. There's a loft antenna there, and it's firing through the loft insulation and the tiles, etc. And the signal is going to the receive antenna. And if we move the antenna outside, as you can imagine, then the attenuation of the signal is less. So outdoor antennas perform better than indoor antennas. And this is because radio waves are attenuated by solid objects like roofs and walls, but less so by glass windows, and that is an item that you may be tested on, the glass window being less of an attenuator than brickwork, as it's mentioned specifically in the syllabus. And the final item to look at then with propagation is ionospheric propagation. And with ionospheric propagation, we're talking about HF. And here you can see then a cross-section, if you like, of the Earth's atmosphere, right up to satellites up in the sky. So we live our lives in the troposphere, between 10 and 15 kilometers, and you can see the VHF communication with that aeroplane flying across the screen. And we don't need to know anything about the Earth's layers for the foundation course. This is just a bit of background. But during the day, when the sun is incident on the Earth's atmosphere, an area forms called the ionosphere. And the ionosphere is between 70 and 400 kilometers above the Earth's surface. And you do need to remember those two figures. Now this ionosphere forms in layers and is a subject of considerable study and considerable interest to radio amateurs, and is dealt with in much more detail in the intermediate and advanced courses. However, we only need some basic facts for the foundation course. So here we have the basic facts. The ionosphere forms between 70 and 400 kilometers high. It's a layer of ionized gas which can reflect radio signals in the HF band. That's between 3 and 30 megahertz. It is dependent on the season and the time of day. When the Earth is tilted towards the sun, there is more energy incident upon the upper atmosphere, and when it is tilted away in the winter, there is less. so there is more ionization in summer and less in winter. And of course, during the day, for a particular region, if the sun is incident on the atmosphere, then it ionizes, and during the night, that ionization dissipates, it fizzles out. So let's imagine here we are, let's say at 11 o'clock in the morning, and we have an ionospheric layer, and somewhere between 70 and 400 kilometers high. And as an aside, I've put some other reference point in. The ISS is above the top of the atmosphere. It's about 408 kilometers high, and geostationary satellites, like the ones we watch for television, are 36,000 kilometers high. So there's a big range we're talking about here. That's just for interest, not part of the foundation course. So returning to ionospheric propagation, there we have our ionized layer between 70 and 400 kilometers high, and a signal from the right-hand side there from an HF station comes to another station, may then hit the Earth, and then may be re-radiated for a second hop. And that's how we achieve worldwide communication on HF. So the sky wave there may have gone over a distance, let's say, of about 4,000 kilometers in a single hop. So, for example, we're able to speak to the United States of America quite easily, with many opportunities to do so from the UK. It's also worth mentioning then that that is the main propagation mode for HF for long distance, but other propagation modes exist. So from the source there, the transmitter on the right, to the sailing boat, over a short distance a ground wave will also propagate, but that will be attenuated with distance and won't go over the great distances that the sky wave does. That's because as it passes over the ground it attenuates, and although it diffracts and follows the curvature of the Earth better than VHF, it still won't completely hug the surface of the Earth, and the signal will diverge from the surface and then be absorbed in the atmosphere. So the ground wave forms a way of communicating as well. And many amateurs will have nets on HF and will use ground wave as their mode of propagation. So these are sort of chat groups, perhaps on a Thursday evening, perhaps on 10 meters, and the amateurs will be quite far apart, further than they would be able to communicate with VHF, but they'll use the HF ground wave to talk to each other, not the sky wave. However, the sky wave is the main mechanism for international communication, or DXing. Now, between where the ground wave peters out and the sky wave lands is the skip zone or the dead zone. Again, not required for the foundation course, but just to complete the picture there. So we've covered perhaps more than we need to in this propagation video. So let's go back to the syllabus now and just recall what we have learned and what we needed to learn. So the propagation basics. Recall that radio waves travel in straight lines unless diffracted or reflected. And we've covered that. We realize that those are the two main mechanisms, diffraction or reflection. That diffraction is dependent on frequency, and that's about it, I think, for those two. Recall that radio waves get weaker as they spread out, and that's a spreading loss that happens to all radio waves. It doesn't matter how well you focus the beam; it can never be parallel. It always spreads out a little bit as it travels out from the transmitter. Recall that at VHF and UHF hills cause shadows, and that waves get weaker in penetrating buildings, but glass windows are more transparent to radio waves. We looked at the shadows caused. We saw that the VHF wave had greater diffraction over the hilltop, and therefore the shadow was smaller at VHF than UHF, but nevertheless there anyway. And we looked at the internal antenna and the external antenna, and we remind ourselves that glass windows are more transparent to radio waves than the fabric of the building. Recall that the range achieved at VHF or UHF is dependent on antenna height and a clear path and transmitter power. So antenna height then, the greater the height of the antenna, the greater the optical line of sight. And remember that our signal goes slightly further than optical line of sight because of diffraction. Remember that if we don't have a clear path, we have attenuation. That is the weakening of the signal due to absorption by objects in its path. And recall that the transmitter power then is important. If we have greater transmitter power, we will have a greater signal at the other end. But we should remember that, and this is a syllabus item, understand that higher antennas are preferable to higher power as they improve both transmit and receive performance. Recall that outdoor antennas will perform better than indoor antennas. Recall that at VHF, UHF, range decreases as frequency increases, and that in general, VHF, UHF waves have a range not beyond line of sight. Now the reasons for the decrease with frequency are a little bit complex and dealt with later on in intermediate and to a certain extent in advanced as well. But that's something to remember. It uses the recall keyword. So basically, as you go up in frequency for VHF and UHF, the range decreases as the frequency increases. And that in general, VHF, UHF waves have a range not far beyond line of sight. So that only leaves us to look at HF. The basics are all that we require. We did have quite a look at the ionosphere, but the key fact here is that it comprises a layer of conductive gases. You need to remember that. They're made conductive by the ionizing effect of the solar rays that hit the Earth. And they are at heights between 70 and 400 kilometers above the Earth. And recall that on most HF communication relies on the waves being reflected by the ionosphere. Now we looked at the ground wave and we looked at the skip zone. Those facts are not required. We just need to remember that most HF communication relies on the waves being reflected by the ionosphere. And recall that HF can provide worldwide propagation depending on how well the ionosphere bends the waves back to Earth. Now, sometimes the ionosphere is not very effective at doing this, and sometimes it is. And there's much discussion about this in amateur radio circles. And the mechanisms for this are dealt with in the intermediate and advanced examinations. But we just need to remember that the worldwide propagation depends on how well the ionosphere bends the waves back to Earth. And the main point here, recall that this varies with frequency, time of day and season. We talked about time of day and season. We said that during the day the sun is incident on the area of ionosphere above us, and so or maybe between us and the receiving station, and that in summer you get greater ionization of the upper atmosphere. So that's an important thing to remember. Also, and we perhaps did not discuss this, it varies with frequency. So if the ionosphere is only weakly ionized, we can select different frequencies from if it's heavily ionized to achieve our goal of long-distance communication. So that's the final point. Recall that this varies with frequency, time of day and season. And I think that just about sums up this video on propagation. I hope you've enjoyed it. And in the next video, we'll be looking at EMC, electromagnetic compatibility. So thank you once again.